Awesome, thank you. How's everyone doing today? Good? Do you have a good Halloween? Yeah, all right, yeah. Anyone go trick-or-treating? Does anyone's residence hall do trick-or-treating or anything? No? Oh. Anyone hand out candy to anybody? Go to a party? Did anyone do anything? You studied? All right, you know what? I'll take it. A win's a win. All right, well, this will be our little Halloween celebration then. All right, so this has nothing to do with anything other than Halloween. So that's all this is. There's no big lesson to be learned from this. Yeah, it's just a bit of fun. So in here is going to be our potassium iodide, soap, and some food coloring to make it a little bit more fun. And then this is hydrogen peroxide. So what's going to happen is we're going to rapidly generate hydrogen gas. And we ready? Yeah. Oh. Woo! Yeah. Yeah. So since we were making hydrogen gas, and then we had soap in there, mixed all the bubbles, and so now we have a puking pumpkin that's just gonna hang out for the rest of lecture. That's it, yep. All right, so it feels like ages ago, but we left off looking at synthesis problems. And so we were talking about this general process of how we can start to break apart our molecules and propose a way to build them back up. So we had said that you want to first identify what is different, then think about that reaction toolkit. How do you know how to assemble your molecules? And then try to think about the order of operations needed in order to make that actually happen. So we had said that some initial reagents, like for our sodium bromide, it wasn't a good match for our original starting material. So that's why we have all of the different options, because you might find one that's a better match, right? And actually, before we get back into this, does anyone have any questions before we get started? So we know our exam is next week. On Wednesday, it's in that same building as last time on the med campus. I'll post another announcement just like we did it'll actually just be basically, I'm just gonna copy and paste the exam one, preparing for exam one announcement, but I'll do it again, just as a reminder of where it is, when it is, all of that jazz. And then reminding you that you can have a model kit if you want it, something to write with, all that normal stuff. And then there is no recitation next week. So Tuesday is election day. So OSU is saying that everything should be either canceled or asynchronous. So we've just canceled recitation, just so you have the day off. Yeah, I think that's all my announcements. Are there any questions about anything now that we've done announcements? Okay, cool. All right, so for the synthesis, we had said that some reagents weren't good matches. So you always want to like check yourself, do the forward and make sure that it works. And there are more than one correct answers. So you want to try to like really, think creatively, because you might need a certain number of steps. Like if you only want one step, then that PBR3 could be better. Or if you need 2 steps, then, or it doesn't matter your step count, then yeah, you can pick different ones. All right, so we're gonna do this next practice problem. And we have to think of our starting material and the steps to get there. So this is like our hardest level question that we could expect, because we don't really have that much of a hint. The only hint that we have is a molecular formula. So if we remember our degree unsaturation formula, then we could calculate that. That'll tell us how many unsaturations we need. If we don't remember it, then that's fine. We can also just do a guess and check, basically. So this is the kind of level of molecule I would give you. So it would be a small molecule, so that guess and check would be easy, basically, is what I would do. So if I just start with 2 carbons and my OH, then does this match that molecular formula? No. What's wrong? Too many hydrogens, right? Because I have 3 plus 2 plus 1, so that's C6. So if I have 6 hydrogens here, but only 4 there, what does that tell me? I need 2 less, yes. So I need to lose 2 hydrogens. How do I do that? We could make a ring, or we could make a pi bond. So that's an unsaturation. Remember, every unsaturation is the loss of 2 hydrogens. So that tells me that I'm only gonna have 1 ring. I mean, it's a small molecule. We couldn't have more than 1 ring with that few elements. But, so we know we have to either have a ring or a pi bond. So that's that level of like, if you don't remember the formula, why I said it would be okay, because you can do that same process of like, do a quick draw what it is if it's saturated, figure out how many you would need if it's saturated, and then just see how few hydrogens you have compared to it. So if I'm thinking about a ring, my options are an epoxide, because the hydrogens can't be in the ring. So that is the smallest size ring that I can have, is 1 oxygen, 2 carbons. My other options are going to be that enol. So I have an alkene with an alcohol. And then I also have an aldehyde, right? Those are kind of my 3 options to have 1 unsaturation with a that molecular formula, because you either have 1 ring or 1 pi bond. All right, which of these can we immediately get rid of? Because it's not stable. Yeah. So actually not the epoxide. The epoxide's actually okay. The epoxide does exist. You're right, it's highly reactive, but it can exist. There's something that's even more reactive, even less stable, yeah. Say it again? Yeah, that vinyl alcohol, yeah. So that enol, remember that we said the enol readily tautomerizes to that carbonyl. So we never actually see the enol, right? So really, we have 2 options. So now we have to figure out, okay, so which one is going to be a reasonable set of, or reasonable starting material? to get to this final product. So we want to try to think about what is different. So we are looking at what sorts of things, like what do I know has to change? When in doubt, do the chemical inventory. We need more carbons, right? So we have 1, 2, 3, 4 carbons in the product, but only 2 carbons in the beginning. So yeah, we absolutely have to, so if we're doing like the one, what's different? You have to gain 2 carbons. What else do we have to gain? What other elements are different? Chlorine, right? I have to gain a chlorine. I don't have a chlorine in the beginning, but I have a chlorine in the end. So I have to gain a chlorine. What else do I have to lose? I have to lose that oxygen, right? There's no oxygen in the product. And then I also need to lose my unsaturation, right? This is saturated. This has an unsaturation, so I have to lose the unsaturation, or you could think about it as we have to gain the hydrogens. But recognizing that we have to lose an unsaturation might help us identify which types of reagents we want, right? Because if we're losing the unsaturation, is that going to be oxidation or reduction? Reduction. It's a reduction. You can also recognize the fact that we're going to have fewer bonds to oxygen. We're going to lose all of our oxygens. But we are gaining bonds to hydrogen, so that is going to be a reduction. So that means that we're probably going to want to pick a reagent that we saw as a possible reductant, right? So next up, we want to think, how can we do that? All right? So what reagents do we know that could add carbon? Yeah. Yeah, we could do a Grignard. Is it weirdly dark in here? I'm gonna make it a little bit brighter. Okay. Sorry, it just felt like really like mood lighting, and I don't know if anyone else was getting really tired, but I was getting tired, so sorry. I need to turn the lights up a bit. All right, so for our reagents, can we still see the screen okay though? Is that, okay. So for our reagents, yeah, we could absolutely, so I'm just gonna do label generic A, because it was the first one we talked about, was adding carbons, was having a Grignard. So that would be like ethyl magnesium bromide. That'll add my 2 carbons. Make life easier on yourself. Pick the reagent that'll add as many of the elements as possible. So instead of doing 1 carbon at a time, if you need 2 carbons, pick a reagent that has 2 carbons. So that way you're just adding both carbons all in one go, right? So what was the other carbon nucleophile that we had? It was the Grignard or the... Yeah. Yeah, the alkyl lithium. Right? So it's either having the MGBr or the Li. So the Grignard is with the magnesium bromide or halide. It could have been magnesium chloride, magnesium iodide, whatever halogen you like is totally fine. Typically bromine is the one most people use, but that doesn't matter. Or we have ethyl lithium. Beautiful. So we know that that will add our 2 carbons that we need. Okay, so thinking through what functional groups did we normally then create after adding in those reductants? Like what was normally our product after adding in a Grignard or the alkyl lithium? Alcohols, right? So that means we're probably going to make an alcohol in our synthesis. So then I'm thinking, okay, if I know that these make alcohols, which I can also double check myself by thinking through the reasonable starting materials, but if I just remember these tend to make alcohols, then I want to think, all right, well, how do I know how to turn an alcohol into a halogen? So this was the reductant that adds 2 carbons. And now we're thinking, all right, how do I make an alcohol become a chlorine? Yeah. Yeah, we could absolutely use thionyl chloride. What else? Yeah? Yeah, phosphorus trichloride. Yeah, we could do PCl3. What else do we have? Yeah. Yeah, HCl. What else? How else do we turn alcohols into halogens? That one, right? Yeah, yeah. The triple chloride, turn our alcohol into a good leaving group to that sulfonate. And then we could do sodium bromide, well, sodium chloride, because we want chlorine. So we still don't want to do sodium chloride because of the exact same reason for the sodium bromide, that turning an alcohol into the halogen, you don't want to just use the halogen, or yeah, the halide directly. So we still would need to do 2 steps, but that's still another option. So we couldn't do NaCl directly, but we could do like the triple chloride, mesyl chloride, tosyl chloride, so MsCl, TsCl, or TfCl. Any of those will turn the alcohol into really good leaving groups. So those are all of our different options. All right, some of them might be better than others. They might all work here. I don't know. We're going to now have to start to assemble it and check. So when we go forward, which set of steps do you think you want to do first? Do you want to do the reduction first or the alcohol to chlorine first? Yeah. Yeah, why the reduction first? Yeah, so remember that the reduction was what actually made the alcohol. And also think about the fact that we need the chlorine at the very end. So if the chlorine is what we see at the very end, we're probably going to be adding it at the very end, right? So that's not always the case, but that's probably how we're going to do it. So that alcohol is probably the alcohol is what's made from the reduction, but also that chlorine from an alcohol, like that's probably going to be our second step. So we're going to then have to now say, all right, if these are my two options, let's try to do one of these first. So do you prefer Grignard or organolithium? Which one's your favorite? Anyone have an opinion? Grignard? Cool. Me too. All right, so now we're doing step 3, which is check the order. So we have that epoxide that someone mentioned first, and we have our aldehyde. So we used our critical thinking skills. We used logical reasoning to say that we're probably going to do the reduction first, right? That's how we picked our Grignard first. So if I do my ethyl magnesium bromide, and if I do that, what do I need as a second step? Every Grignard needs that acid workup, yeah, that HCl and water. So I'm just gonna put this in to make sure that I don't forget it when I'm proposing my full synthesis. And also, what's a reasonable solvent for the ethyl magnesium bromide? Yeah. Yeah, THF, beautiful. How'd you pick THF? Yeah, it's an aprotic solvent. So I needed something that isn't going to be acidic, right? That's the most important factor, because that Grignard is basic. So I can't have something that has a proton, because then the Grignard just reacts with the solvent and not my desired starting material. So I need an aprotic solvent. That's the most important factor. So which aprotic solvent? I don't particularly care. THF, beautiful. That's a great pick. That's actually a very reasonable pick. That's something that most people will use in a lab. But if you picked any other aprotic solvent, I'm happy, because you recognize the inherent reactivity that that Grignard is basic, so you need an aprotic solvent, right? That's the crux of it. That's the important thing. All right, so we said that we're going to do that, so we'll have that be our same steps for both, because we still don't actually know which starting material we need. So then now we have to think about what is the product of each of these steps. So what is my product of this first addition into the epoxide? So close. So you've identified the radioselectivity correctly. You recognize that the alcohol's on the end, that's honestly the hard part. The second thing is you want to make sure you're counting your carbons correctly. So I think I heard you say pent. Pent means 5. I only have 1, 2, 3, 4 carbons, so it'd be bute. So butane 1 all, but that was excellent. So what we're recognizing is this Grignard is going to come in, attack one side of the epoxide. Both sides of the epoxide are equivalent, so whichever one you pick doesn't matter. But it pops the ring open. So when it opens that ring, you get your alcohol on one side and the ethyl on the other. right? So if this is 1, 2, you get OH, 1, 2, ethyl. Which is also that thing. What's our product if we do it with the aldehyde? Yeah. Yeah, that butane 2-ol. So what we're recognizing is that when you add the aldehyde, your Grignard adds to the same carbon that keeps the oxygen, right? So that your nucleophile and your oxygen are attached to the same carbon, whereas before, the nucleophile and the oxygen are on separate carbons. So now that can help us know which product we want, or which starting material we want. So this gives us this product, which is this thing. So then if we do, so this was A. So if we do B next, and the first suggestion that was made was thionyl chloride, so I'm just going to do that one. What's a reasonable solvent for thionyl chloride? Think through what mechanism we need. So thionyl chloride, which mechanism did it act through? SN2. So if it's SN2, what solvents are favored in SN2? Aprotic. So which solvent do we want to use? Yeah, an aprotic one. Which one? DMSO? Cool, that works. Yeah, sure. So typically the one that's used is like DCM, the dichloromethane, but I don't care. This one, beautiful. It's aprotic. So that works for the mechanism that we want. So that would, picking DMSO will absolutely get you full credit. If you're looking on an answer key, you probably will see DCM. That's also fine. Like if you, or you could pick THF or diethyl ether or 1,4-dioxirane if you're feeling really, I don't know, whatever. Yeah, I don't have an adjective. If you're really wanting to, whatever. You can pick any aprotic solvent, and that's beautiful. Because I want you to recognize that's an SN2 mechanism. SN2 favors aprotic solvent, so then it's just pick your favorite aprotic solvent, right? So the one in the book or the answer key might be different, but your answer might still be correct, right? That's the point that I'm trying to get at. So then when we do that, it's going, because it's SN2, it's going to directly replace the alcohol with our halogen. And so then what do we see? Which starting material do we need? And maybe it was obvious after the first step, but what's our starting material? The epoxide, right? because that's the one that actually leads to our desired product, right? That's where we're trying to get. So that means that the epoxide is where we had to start, and then these are our steps in order to synthesize it. So when you would go to write your final answer, you would put the epoxide in the box for the starting material, making sure that we match that molecular formula, just one last double check, and we're like, yep, that's good. We have 2 carbons, 4 hydrogens, 1 oxygen, tick. We at least know that we drew that molecular formula. And then we would number our steps. So we would do that ethyl magnesium bromide first with our THF, was our aprotic solvent that we wanted. Then we would do our acid workup with HCl and water. And then we would do thionyl chloride and DMSO were the solvents that we picked. So one thing to note is that we do want this to be just an acid workup. So you could write dilute. If you want it, well, you would write HCl, HCl is dilute. You don't have to, but you could if you want to. But you want to make sure it is an acid workup, because if you have like excess, a lot of students will try to write excess and have that be their like last step to get directly to the chloride. That won't work, because remember, you're in water. In water, water forms a tight solvent shell around chlorine that makes your chlorine non-nucleophilic. So this step will not take you directly to the chlorine. This step will stop at the alcohol, because the chloride here is not nucleophilic because it's in water, right? Does that track? Okay. So this is just an acid workup. Because chloride is not a nucleophile in water. If we're feeling really jazzy, and if what I'm about to say confuses you, disregard it. But if you're feeling really like adamant that you're like, I want this to be 2 steps only. I want to ensure that I can just use HCl. Like, I'm steadfast adamant it must be HCl that is going to turn my alcohol into the chlorine. Then what you want to do is you would still do your, step 1 is your ethyl magnesium bromide. For step 2, you would have HCl, you would make it excess, and then you would need to have an aprotic solvent. So you would have some sort of whatever aprotic solvent makes you happiest. So if we did like DCM or something, whatever. And then you would need a desiccant. So you would need something like a Dean Stark trap, which actually wouldn't work for this one, but that's fine. Or silicon dioxide, which like, that's your, the little packets that come in when you buy a new pair of shoes or something, or a new purse, or new anything, any technology. There's usually like some little packet that you can shake and it has a little like maraca sound. Yeah, that's usually silicon dioxide. The point of it is to absorb water. So the whole point of this is you would add something that would absorb the water so that it takes water out of the equation so that chloride can be a nucleophile. So this is like, if you're adamant that you're like, no, I must use HCl, I need, like, I can't think of anything else. I have to brute force make this happen in 2 steps. Then you could have your HCl be both the workup and be your next reagent by showing it in excess. But you just need to make sure you have a desiccant because you got to keep water out of the equation. Otherwise, you'll always go back to the alcohol. And we could have absolutely swapped out the Grignard for the ethyl lithium. That would also be a fully correct answer. We could have picked any of the other options as well. All of these would also be absolutely correct answers for reasonable reagent swaps. The HCl, the same issue was you need a desiccant to remove the water that you make. You need something to get rid of the water because chloride in the presence of water is not a nucleophile because it forms a tight solvent shell. You get the bubble surrounding your chloride and the chloride can't react. Which is why I usually just pick thionyl chloride as my favorite. So I'm like, if I know that I need to go from an alcohol to a halogen, I'm doing thionyl chloride or thionyl bromide. That's just, those are my faves. Or I'll do PBr3 sometimes if I'm feeling jazzy. All right. Are there any questions about how we're applying that process to that? Like, this is the harder example, yeah. So if you're using, so if you're using the HCl, you could use THF as well, yeah. So you would just need a product. So yeah, I chose DCM. You could have done THF or. Well, I ran out of space. Any A product. Yeah, that's a good point. So the reason that HCl is usually shown with water is because it's extremely hygroscopic, meaning it just loves water. Like, it doesn't actually exist on its own as a liquid. So HCl gas is a thing, that's pure HCl. But HCl concentrated, like when you have the most amount of HCl as a liquid as possible, it still contains water in solution. It just loves water. It reacts really tightly with water. So it's actually always sold as a mixture. And so it doesn't actually exist just as pure HCl. That's why you usually see HCl with water, or you'll see HCl aqueous. Even when it's concentrated, it's just that's how it exists. Any other questions about this synthesis? Okay. Does the process make more sense? The more you practice the process, the faster you'll be with it. And you can find more practice problems by looking at previous exams, looking in the textbook, looking on Achieve in the dynamic study modules, looking in the homework in the practice exam problems on Achieve. I also have linked out extra synthesis problems in the weekly outlines. And then Dr. Baldwin also has extra ones that she has in hers if you like her problem sets. So the more you practice it, the easier it'll become. But the main part where students get hung up is, well, actually all of it, but the main part where students get really frustrated is that they can't remember what reagents will work. So they don't remember what their options are. So you want to think about inherent reactivity. So you can do synthons. We didn't do synthons here because we didn't have a starting material, so it was a little bit harder. You could have done a synthon, but it kind of would have been a little messy, so we just didn't because it's just harder. But you want to think about the inherent reactivity. So actually, if we had done synthons here, we could have, because both of these are electrophiles. So no matter what, I recognize that my starting material is an electrophile, so I needed a nucleophile that I was adding in step A. Right? So like that same process can help you to think about the inherent reactivity of it. Okay. All right. So let's do another one. For this next one, I want to give you, let's see how much time we have. I want to give you like 5 minutes. I know that's not enough time to do this for like the first time you're seeing it. If this were on exam, I would imagine it would take you probably, let's see, it's normally about a minute a step is how I kind of think about it. So it'd be like 1, 2, 3, 4, 5, 6, 7, 8, 9. I would expect you to probably have to spend about 9 minutes on an exam to do this, which is why this question would usually then be worth like 20 points or something, where each step is like lots of partial credit as you go. But so I want you to think about where we're starting, where we're going, and try to think about what changes need to be made in order to get there. And then we'll think through all the independent steps. So I'll give you about 5 minutes to try to get as far as you can, and then we'll regroup to work through it together in the last 10 minutes. Okay. So, like I said, I don't expect you to actually have a complete answer at this point, but hopefully you figured out kind of where to get started. So when we're looking at this, what I like to do is something that I call mapping onto the product. So when I'm mapping onto the product, what that means is I'm trying to keep as many elements the same and in the same place as possible. I'm trying to make things as easy on myself as I can. So that way I'm not trying to move everything. I'm not trying to break every bond, make every bond. I'm trying to see what can I keep exactly the same so that I can also help me see what's different. So, because initially when you look at this, I don't know about you, but I look at this and I go, what's different? A lot of things. And like my brain kind of starts to shut down because I'm like, I don't know, all of it. So when I get stuck, then what I say is, okay, instead of trying to find what's different because there's a lot that's different, let's start by finding what's the same. So I'm gonna look for, all right, where do I see this dashed methyl line wedge methyl? And I see dash methyl line wedge methyl. And I'm like, okay, cool. That's the same. So those are probably the same 4 carbons. And then I see, okay, where do I see an oxygen attached to it? Right there on the left side. So that means I'm probably keeping that left side of the epoxide so that I can keep that same oxygen. So then that helps me see, oh, well, what I didn't highlight is this methyl that's on the oxygen. That's new. This wedged methyl at the alpha carbon, that's new. And then this cyclopentyl, that's also new, right? So that helped me by mapping onto the product, by trying to find what is the same. And to be honest, normally what I'll do is I'll look for something that's the most unique. So the fact that I started with the dash methyl here, I did that actually kind of as a guiding hint to try to identify where the methyls are the same. Honestly, what I truly do is I look for heteroatoms. I would have looked for the oxygen first. So I would have gone oxygen, and then I would have tried to find where do I have a bunch of carbons then attached. So I would go down and be like, okay, oxygen, oxygen. I'm gonna hope that's the same oxygen. And then I find, okay, there's carbon, more carbons if I go down. So I'm gonna guess that this is down. And then because I see the dashed methyl, then a wedge, that's why I assume it's the left side for the dash, then the wedge. Because if I went this way, I could have seen the wedge methyl, but then I don't have the dash on the other side, right? So that was kind of my hint to be like, okay, that's why I'm looking for this mapping out this way. Okay, so now I've identified what's different, is I recognize I need to add a methyl onto the oxygen, I need to add a methyl to the base of the oxygen, and I need to add a cyclopentyl to that carbon. So we want to think about how can I do that? So when we go to think about how, if you write everything out in the list steps, that can take a lot of time, but if it helps you, do it. But instead, if you can start to do, like here, I recognize, all right, so how do I know how to add this? I know that I know that I can add the Grignard. So I'll be like, all right, how do I add this? It's with that cyclopentyl MgBr, or lithium, whichever one's your favorite, with then the acid workup. So I know that I can add that carbon chain with a Grignard, because that's how I know how to make carbon-carbon bonds. So same thing, because this is a carbon-carbon bond. I'm assuming that this is probably going to be, and again, Grignards I just like, so I'm gonna keep doing Grignards. That could be a methyl magnesium bromide. Could have been a methyl lithium if you really like methyl lithiums. So I'm recognizing that it's a carbon-carbon bond, and the only way that we've talked about adding carbon-carbon bonds is with that Grignard organolithium. So that's my key hint here that I'm seeing. When I look at this top one, that's not a carbon-carbon bond. That's a carbon-oxygen bond. So Grignard wouldn't be reasonable here. What is reasonable is that this oxygen would be a nucleophile and that this carbon would be an electrophile, because I'm recognizing it's a polar bond. So the Grignard does carbon-carbon, But I could just add, if I just make this a leaving group, I could add like methyl iodide. With that O minus, and then that will alkylate that, right? That's how I make those polar bonds. The oxygen-carbon bond is that the oxygen can be a nucleophile, and then I'm just adding in the electrophile, because here I want an electrophilic source of carbon, as opposed to here, when I'm trying to make carbon-carbon bonds, I need a nucleophilic source of carbon. So then that's how we can quickly identify our reagents. So then we also need to think about like, okay, well, how am I going to go about doing this? So if these are my options, if I make this A, B, and C, so if I do A first, so I'm adding methyl iodide, what happens? We'll do it this way. Keep our reagents on top. There's no reaction, right? I just added an electrophile to an electrophile. That's a bad match. You want a nucleophile with an electrophile. So our epoxides are electrophiles, so I don't want to add an electrophile right away, right? So this is an electrophile, this is an electrophile, so that equals no reaction. So I'm not going to add that methyl iodide first. So then we're going, all right, well, let's, I'll keep it red since I already started red. All right, well, what if I do my option B next? My methyl magnesium bromide. Because I know that I want it on the left, I'm just going to imagine it adds to the left. Because it's symmetrical, it technically doesn't matter, it could add to either side. But because I'm trying to map onto the product, make it look more like the product, if that methyl magnesium bromide adds in, remember the oxygen ends up on the opposite side of where your nucleophile adds. So now I have my methyl here, and my oxygen is on the wrong side, right? Because I want that methyl and the oxygen on the same side. So this is, you know, probably not what we want to do. We need to instead consider option 3. So if you were stuck, let's say you wanted to, like you only had A and B, well then B's your only option. You got to try to come up with new creative ways. But because we have a third option, we're just going to hope our third option is easier and actually takes us on the right path. And so then that's what we would do next. So did anyone see that they needed to add that cyclopentyl Grignard in first? Yeah, a couple of people? Awesome, good, good, good. This is hard. So if you're like, no, that's fair. Like, it's hard. You want to practice this because this is definitely, like, this is absolutely something you can expect to see on the exam. So you want to try to practice identifying the bond connections that you're making. So that's where we're seeing that cyclopentyl add in. And it, again, I'm just drawing it on the right-hand side because I know that I want it on the right-hand side. So I'm mapping onto the product. I'm just making it look like the product. Okay, we are out of time. But what I'll do is I will finish writing out the solution before I upload the notes so that you can look at it. And then when we do our review session on Monday, I'll start by kind of finishing the discussion, answering any questions about it. Does that sound good? Cool. Do try to look at it before Monday, though. All right, have a wonderful weekend. And stay healthy. There's a lot of diseases going around. Wash your hands. Get sleep. What's up?